Awesome. Okay, cool. Well, thanks for having us over here. Today I'm going to talk about no instrumentation, Go logging with eBPF. This is a fairly technical talk, so please feel free to stop me and ask questions. Just unmute yourself and ask away. Awesome. Okay. So I'm Zain. I'm the co-founder and CEO of Pixie Labs. I also teach at Stanford. Before this, I used to be at a bunch of other companies like Google AI and NVIDIA, mostly working on machine learning technologies. So with that in mind, let's just dive right into it, and then we'll go from there. So kind of the problem that we're looking at solving is typically, you're an application developer and you have a problem with your program in production. Right. So what you normally do, right, is like, okay, there's like no issue with this. You just go take a look at the logs and you can go figure out what's going on and then debug it. What typically happens, though, in reality, is that the logs aren't in the spot you want them to be in. And I think we've all been there. We kind of want to understand, like, what is going on inside this function? Like, what is this variable value whenever the function is called? What are the arguments? What are the return values? What is the function doing somewhere in the middle? So when you're doing this on like development, what people typically do is use a debugger. And I know not everyone like religiously uses debuggers, so I'll just do like a quick walkthrough of what a debugger is and how the debugger works. So if you're doing Go, you're most likely using Delve, right? Delve is one of the primary debuggers for Go. You can also use something like GDB, but it has less support for the Go runtime. Which means that you don't get as much visibility into the data structures and also like what the current state of the entire Go runtime is. So the first step to use Delve is, basically you just go get it. It's very easy. There's this little test application that we're going to be talking about in the context of this entire talk, including how to use Delve. The test application is basically an HTTP handler that calls this function called compute E. Which basically computes the value of E using an approximation based on the number of iterations you pass it. It's not really important how this works, other than the part you have a function, you're passing in a number of iterations, and it returns you an approximation of E. So with that in mind, if you wanted to understand how Delve works, you would go through and run it. So the way you start Delve is you say Delve exec app, and then basically Delve will run the app and attach to it. If you press C, you can press B and then type in a line number, and it will basically set a breakpoint. A breakpoint is where the debugger stops the code from executing and then allows you to inspect the current state. So I've shown this on the side over here. When you do a breakpoint on line number 15, which happens to be in the middle of this function, for reference, line 15 of the code happens to be in the middle of this for loop. It'll basically stop execution over there, and then you can go print out, iterations or the value of I, and then inspect the current state of the system. So far, so good. Any questions so far? Okay, cool. So the other thing debuggers are really good at doing is giving you a lot of context. So the first thing you can do is you can use this thing called BT, which stands for backtrace. And what that tells you is the current stack of the system. So it'll tell you where is it and how did it get over here. So in my compute E function, it's pretty simple. It says main.compute E. The previous function it says is main.main.func1, which I haven't shown you the rest of the code, but it's basically the anonymous function that goes inside of the HTTP handler. Right, and then before that, it says in the serve HTTP function. The other thing you can do is you can type in GRS to get a dump of Go routines. So this is all like pretty simple debugger usage. And if you haven't used Delve, I'd recommend you check it out and play around with it. It's a really nice debugger. So just as a quick recap on this, debuggers provide you an easy way to get information about code that's currently executing in the system, right? One of the main benefits of this is, there's no need to add like a print statement and then recompile and run it, which is usually like, when we all start writing code, that's the first thing we go to, right? It's like, we're like, oh, what is it doing? I'm just going to print out the values. This is like one way to avoid like the recompile loop. The other nice thing is like Delve and GB can connect to remote binaries. So you can help, so it can help you debug debug programs that are running on, a Docker container or some other machine hosted on a VM. Unfortunately, it's a little bit harder when you're running in things like Kubernetes, but there are tons of tools like Solo and stuff like that that make it pretty easy to use. So I recommend checking those out. So the question is, let's come back to our previous thing is, let's say you're interested in production code. Debuggers are great when you're running in your debug and local environments, but what about running them in production code? So it turns out you can still attach debuggers to production binaries using the remote function that we talked about. Usually this is not such a great idea because one of the things about debuggers is that they can mutate the current state of the program. In particular, they also stop the program from executing. So most real production code has tons of like timeouts and other things to make sure it doesn't get stuck. And since they stop the execution and mutate the state, you can get unexpected failures that have nothing to do with what you're looking at. So you probably don't want to do this on prod. So if that's the case, what else can we do? Well, we're back to our options. So the first option is, well, just go back and add locks to your program, recompile and redeploy it. This can be like your simple log statements or more comprehensive things like open tracing that allow you to go across machines. Option 2 is, well, you can say, well, I don't care if it messes with my program. I'll just attach GDB or Delve and see what happens. And you can do that. You can try using one of these Linux tracing utilities like strace, ftrace, or USDTs. And they have their benefits and can work, but they're a little bit annoying to use. The fourth option is to use this thing called eBPF, which stands for the Enhanced Berkeley Packet Filter, which seems like a very weird name for something we're going to be using to instrument programs. But I'm actually going to skip this slide, go right into what is eBPF. So eBPF at this point has outgrown its packet filtering system. And basically you can think about it as like a small VM that runs inside of the Linux kernel. So the way eBPF works is that you give it some C program, it compiles it to this BPF target, and the BPF program can be safely inserted into the Linux kernel. So what happens is that the C program is, a restricted form of C. It can be fully verified to make sure that it's a safe program. You can then make a syscall, stick it in the Linux kernel. And once it's in the Linux kernel, it can do things like intercept system calls. And you can also do these things called uprobes, which basically allow you to insert a probe into a user process. There's a lot of stuff to digest over here, so I'm going to take a second and ask if there are any questions, or if you want me to dig into more details. Anyone have any questions?
No, looks good.
Not yet.
Okay, cool. So takeaway from this is think about BPF as a mini sandbox virtual machine that runs inside a Linux kernel. It allows you to do a bunch of operations safely. One of the operations it allows you to do is a thing called uprobes, which allow you to insert probes in the user space programs. Cool. So how does that work? Well, with this, now we're going to go another level deep to understand how that process works. So one of the things is all programs are consisting of these things called symbols, which allow you to basically locate, various functions and variables in your program. So you can use this program called obj dump on Linux, and this will basically dump out all the symbols for your application. So going back to the original application we talked about, we can dump out all the symbols, and then we can say, grep for the compute e function. Sorry, second. We can grep for the compute e function. And over there, we can see that there is this function called main.compute e located at this address, whatever, 6609A0. And it's in the text section, so we know that it's a piece of executable code. If you dump the program out a little bit more, you'll actually see that the first thing it does is it copies over this variable into the RAX register. I won't go into the details, but Go uses this thing called, sorry, I meant to say from the RAX register. Go uses this thing called plan9's ABI, which means that the way it can passes variables between functions is like well-defined using the spec that was done for plan9. So with that, we know that the first argument always appears on the RAX register. Just take my word for it for now, and if you have questions, we can talk about it later. So what happens if you have a uprobe? So if we go back to our binary, we identified this address as 660980, and this is the main.compute function. The main.main function is located right below that. If you had other functions, you'd see them over here as well. So what we do with BPF is that we basically say whenever you hit this address 660980, instead of starting to execute main.compute call our uprobe hook. Our uprobe hook actually calls a BPF program, right? So the BPF program can now do stuff. And one of the things it can do is it can read the register values, and it can basically read the current state of the memory. So after that, there's this concept in BPF called perf buffers, where you can basically write data to and then read it from a different program. Right, so perf buffer is like a location in memory that's basically going to get written to by the BPF program that some other program can go and later read. All of this is in a sample binary, and it's relatively easy to follow, I think. But go with this diagram for now, and we'll get into it. So the next question you're probably going to ask is, what is in this BPF program, and what does it look like? So what happens, as we discussed, is that this function is simply called every time main.compute is called. This is actually the C program on the right side, which basically says, okay, I have a perf output called trace. What I'm going to do over here is every time compute E is called, I'm going to read the AX register. If you remember, the first argument is an RAX. So we are basically reading the AX register right here. And then it says, submit this event to the perf buffer, and that's it. That's all this function does. It basically, every time it gets called, it will read the AX register and submit the value of the AX register to the perf buffer. And what happens outside of this is that we basically register this function to get called every single time compute E is called. I can actually quickly show what that looks like. So again, over here is the program. It's actually embedded as a string inside of the Go program. And what we do over here is that we say that load a uprobe whenever compute E is called. And then the uprobe, this gives you the file descriptor. And then it says attach uprobe to the binary. So one of the things that uprobes do is it'll instrument every invocation of that binary, right? So you just need to know the path of the binary, and then you say for this binary, whenever main.compute E is called, load this uprobe. Cool. So I will continue on for a couple more slides, and there is a demo. Oh, actually, the next slide is a demo. Sorry. Feel free to ask me questions while I pull up the demo. Okay. So what am I going to do here? So I have the application binary. Let me just open it up real quick so I can walk through the rest of it. Okay, this is my app.go. It is, make it bigger. Cool. It is a fairly simple program. Here is the compute E function. And then here is this handle function that says every time /E is called, it'll basically read the value iters, and then it will call compute E, and it will write that to the output for the number of iters. Okay, so it's a pretty straightforward application. So what I'm going to do over here is I'm going to run it. Okay. So just for a demonstration, if I, sorry, I'm in the wrong window. Okay. If I curl this, we can see that it returns a value of e for 10 iterations. If I curl it only for one iteration, we see the value of e is 2, which is wrong. It should be 2.71. So as you increase the number of iterations, the value should be getting more and more accurate. Cool. So that's what the application does. Interestingly, if you remember, I don't actually know when I curl this with no iterations, what is the default value it uses. So let's try to figure out what the default value it uses by running our tracing code. Okay. So there is this binary in here called trace.go. So this is a completely different program. You already saw this on GitHub, but I'm just showing it for a reference again. It basically has this BPF program, and then it attaches the BPF program to the passed-in binary whenever main.compute e is called. Okay, so with that in mind, I will run this program. So trace example, binary, and then give it the path to the application. I think it's my password. Cool. So now that this is running, I will curl it. And oh, look, it tells me that the default value is 100. So I was able to intercept it, capture the value, not stop the program, and then get all the data. For reference, if I run it with some other number of iterations, like 3, you'll see the value is 3. Any questions so far? Okay, great. So that in mind, we can go over here. So one of the things that we kind of go to doing this is that you can use these things called uprobes and trace points to basically dynamically log things to make it easy to actually capture data from production binaries without actually stopping or mutating their state. Unfortunately, the example that I showed is very straightforward because it's basically reading a single value, like a single numeric value, and that's pretty straightforward. It gets a lot more complicated to do when you have multiple arguments, when you have like interfaces and channels, and you have like deeply nested structures, and that makes the stuff very difficult. So part of the shameless plug that I want to add in is one of the things that we've been doing at Pixie is actually making it easy to essentially stick a print statement anywhere in the function without having to worry about how to actually do this. And other related projects are, there's this thing from Kinwolk on Inspector Gadget. You can check out our stuff on Pixie. And then there's a bunch of stuff from Sysig on eBPF.